So before break, I was discussing about brief introduction on the biometrics, and then we slowly move towards challenges in the face recognition system, some unexplored challenges which are still there in the face recognition system, and then towards the presentation attack detection. So we now understand what is presentation attack, how we can generate these kind of attacks. There are several ways how we can do that. And there also exist several techniques. So it may be an hardware-based techniques or it may be in software-based techniques. So now for this second session, I will be presenting mainly on what we did for the presentation attack detection. So at our NTNU, so we are working on three different aspects of presentation attack detection. The first thing is we are trying to address the generic consumer devices. So more particularly, we are focused on face and periocular biometrics. And the solutions are based on exploring inherent characteristics of the device. So that means that given the smartphone with face recognition system or with any other biometric system, so can we deploy a presentation attack detection model that can explore other kind of sensors that are present in the smartphone? So we are not bringing in any new kind of hardware here, but however, we try to see like what aspect of the smartphone in turn can be used to identify the presentation attack. And the second direction what we are taking is on the hardware-based solutions. So we have several custom developed solutions from us. So we have our own custom multispectral sensing and custom hardware, custom 3D sensing that we have used to address this presentation attack detection. And we are mainly focused here on face, finger vein, periocular, and iris biometrics. Both commercial as well as own hardware solutions we try to explore and we try to benchmark like where we stand. And the third is the software-based technique. So of course, the mainstream of deep learning also attracted us to contribute something with the software-based techniques. But what we are addressing here is the presentation attack detection. So presentation attack detection, when we talk about that, we don't have a large-scale data sets similar to the face recognition. So obviously, we are very much limited when it comes to the deep learning. That means that we cannot train our own deep architecture that can perform this kind of task. Rather, we can use a deep learning to act as a transfer learning or to perform and feature extraction. So this is same as what Dr. Dinesh has already mentioned to you in the first talk. So we will be doing the same thing. So we try to see and analyze what type of what type of transfer learning, what type of layer, which layer we can use for the transfer learning, or can we just use the existing off-the-shelf deep learning and do the feature extraction, and then we train our own classifiers and see like what we can how much we can achieve the generalization and so on and so forth. So the most of the analysis what we did is on the image based analysis. In some conditions, in some circumstances, we also use the videos, especially with Kinect and especially with finger vein and so on and so forth. When we have a video, obviously we have an opportunity to use the motion. So motion of the real presentation and the motion of the artifact presentations are quite different. So we have several techniques that we proposed to identify different aspects of this, the different features from both image and the video to perform the software-based presentation attack detection. So I will start with the generic consumer device. So as we try to scale our problem towards more towards the customer-based device, then there are several challenges we come, right? So when we talk about the smartphone, we need to consider the smartphone which is available for lowest price to the highest price. So our solution must be scalable across all kind of smartphones which are available. And also it must be available it must be scalable for different kind of computations we have. So depending upon the type of the smartphone, the quality of the image what we capture is always challenging. So for example, with the low cost smartphone, so we have a frontal camera with less than 1 megapixel or something like that. So obviously we cannot capture a very good face quality images. And obviously when we say we are bringing the solution to the smartphone, of course, the variations in the environment is very huge. So we cannot ask the smartphone user to sit in one place and do the biometric verification, right? So he must be given flexibility to do his biometric verification wherever he want. So once he's doing a biometric verification, then our presentation attack detection scheme must also work under the same similar environment. And of course, there is a challenge of computation resource inside that, and the lack of generalizability is very, very challenging here, because the cameras what we use is different, the environment what we use is completely different. Therefore, when we talk about especially the software-based devices, software-based presentation attack detection, it is very, very challenging to achieve the generalizability. So then what we try to introduce here is, can we use the imaging chain used within the smartphone to identify these kind of attacks? So when we take the smartphone, so in general, we can represent the any face recognition system like this. So we have a face, we have a localized face, we do some features, and then we already have an environment face and we have a comparator. So when we want to bring in the spoof detection or the presentation attack detection scheme, then it should take a path here. Just after your localized face region, then comes our detection unit here. If it is a bona fide, then it will send inside the face recognition system. If it is not bona fide, then it will automatically reject and generate an alarm. So what is our idea here is, can we explore little bit or exploit little bit on the imaging chain of the smartphone? So the smartphone has a camera and it is associated with several processing units. So can we start from the very initial unit of the image capture? So for example, like we have a image captured from the camera sensor, then we can go towards the sensor and we extract the raw image without it is processed or rendered to the user. The raw image means especially at the sensor point itself. Can we add that image and take that image and do some analysis and see, can this kind of image can give some characteristics of the presentation attack artifacts. This is because when we are presenting a photo to the smartphone, obviously the reflections and the other kind of reflective factors on the artifact is very much different than presenting the bona fide image. So if you have a glossy photo which is presenting, then you can see that it is more shining, a lot of reflections is coming up. If you are presenting a display attack, obviously you can see that the light is emitting out of the display. Through the light, there are some unseen waveforms or unseen frequencies coming out of the display light, right? So these are certain kind of noises. Can these noises are captured at the very at the very first stage of imaging? So once the image has been processed and compressed and rendered, obviously these kind of noises are automatically taken care by the image processing chain in the smartphone. So we try to see, can we act right after the image is captured before going to the processing chain and try to see these kind of special kind of noises that we can extract. So what we do is we basically use as an Android smartphone for this experiment. So we have this imaging sensor. We look for the Bayer sensor pattern. So this is straight away on the imaging sensing. And then we have 3 different channels that we extract: red channel, green channel, and the blue channel. Once we extract these 3 different channels, so we can notice that there is some scattered noise around this. So then we try to see that, okay, this noise may be different for the artifact due to the characteristics of the material, and it may be different for the bona fide. So we simply try to use a median filter and extract and filter it out the image and do the subtraction and extract the residual image and then compute the energy in the blocks. And then we simply compare the energy with respect to the decision threshold. So note that we are not using any kind of classifier here. So that is the major advantage of this kind of technique. So no need of classification, just have an analysis on the noise. Based on the noise or the intensity of the noise it generates, can we identify these kind of attacks? So if you look into the images, what we got now, so the first row here is on the raw image from the sensor. So this is the bona fide presentation. So with respect to the display attack here, so we have used display from this is a Dell screen, that is a monitor what we have used, and this is a Samsung phone or the Samsung pad, I believe. So it's a Samsung pad which we have used, and this is a paper. So this is a print attack that we have generated from the Bonafide. So you can see that especially with the display attack, we have a very different kind of frequency that is captured. So this is a emitting frequency from the displays. So due to the light. So here you can see this kind of characteristics. So it is quite realistic that, okay, so we can extract this kind of noise and we quantify this noise and see whether we can get the bona fide. So once we do this simple median filtering and we see that, okay, the residual image is almost zero, it is not zero, it's almost zero, then we have other kind of noises which is still visible. So we use this intuition and then we build our recognition system. So for that we collected some images and so on and so forth. And then we see that with different values of threshold, we have different values of average classification error rate. So the results what we present is BPC here, that is bona fide presentation classification error rate, and other is APC here, that is artifact presentation classification error rate. So bona fide presentation classification error rate means that how many bona fide are classified as an attack, and attack presentation classification error rate indicates that how many attacks are classified as bona fide. But however, what is interesting is to see the ACER, which is average of both. So in most of the cases, you see that the ACER, especially with certain threshold of 25,000, is giving almost a very good results. And we also present there, we also do the scattering plot of this. So all the attack scores should remain in the bottom here, and all the live scores should remain here. So we can see that some of the scores are up and down, but still with reasonable performance, especially on the display attack, can be easily identified, especially if we exploit the early processing chain of the imaging in the smartphone. So another technique what we try to explore is how we can use the focus property presented in the camera. So we know that the focus in any of these smartphone can be varied in a range. So it may not be have a fixed focus, right? So we got a program that can automatically generate a face image with changing this focus. So if you see this image here on my left side, so you see that the focus of the image is changed. So if there is a change in the focus, can we have a 3D with this? So if we can have an approximated 3D, like not at 3, it's 2.5 is quite enough for us to identify the 2D versus 3D, because we assume that our face, the real bona fide, has a 3D structure. However, the artifact, especially the print and the display attacks, has a 2D structure. So our idea is to explore this variation in the focus, and the variation in the focus is related towards the 3D. So can we have the depth from the focus to identify these kind of attacks? So that is what we do. So we compute the focus, and then from the focus we estimate how it is different from the bona fide, and then we estimate the total focus difference, and then again we compare that with the preset threshold. So if you look into the top figure here, so we have a smartphone. By changing the focus in one shot, we get like multiple focus image. We stack them all. We obtain the focus stack. We align the stack, and then we compute the focus for the each. From the each focus point, for the each frames, we obtain the difference of the focus by comparing it with the preset focus computation, and then we obtain the total focus and compare it with the threshold. So this is a qualitative result. So you can see that if it is a real, the structure of the 3D is more visible here. And if it is an attack with the screen or attack with the print, so that means that the 3D versus 2D can be easily differentiable just by manipulating the focus in the given range. So we have done some experiments on this, and then we identify that for some of these presentation attack instruments like display phone and so on, we have achieved a very interesting, almost like zero results in, especially for the phones and so on. But still, the display monitor is as a challenging, because we had this bent kind of monitor, so a small 3D structure was also identified. So other kind of the hardware approach what we try to use is on introducing a light field camera for presentation attack detection. So the main advantage of using light field camera compared to the conventional camera is this camera will record the direction of the light falling on the sensor. That means that you can you can not only record the intensity, you also record the direction of the light. From the direction of the light, you can obtain the different focal image. From the different focus image, you can construct a depth. And all this can happen in a single shot. It is just like a click camera. So any camera what you have used with your smartphone, but this dedicated sensor, you have like one click and then you get a nice 3D rendered with this technology. So this is called as a plain optic technology. So when compared to the conventional camera, so this camera is with multiple micro lenses we call. So as the light passes through the main lens, this light is allowed to scatter across the multiple micro lenses so that it can record the direction of the light. With respect to the direction of the light, multiple focus image can be retrieved. So once we have this multiple focus image, obviously it is quite easy for us to classify the bona fide because the bona fide is assumed to have a 3D, whereas the artifact is assumed to have a 2D structure. So we collected a large scale database with different kind of printers and so on and so forth, and three different kind of attacks we have performed, like two different printers. One is the laser, which is a kind of low quality print attacks. Another is an inkjet print, so which is a extremely high quality print attacks. And then the electronic display with some iPad and so on and so forth. So once we generate the database, it is always important to verify it with some commercial face recognition system to make sure that the artifact what we have generated or the attacks or the presentation attacks what we have generated is strong enough to deceive the face recognition system. So if you recall, I already mentioned that the face recognition system always run with a quality estimation. So if your attack image is not enough to cross the quality estimation, obviously we don't need any kind of presentation attack detection schemes. So what is quite important is we need to have this vulnerability analysis, especially on the commercial system. So that is what I am presenting here. So we did a vulnerability analysis. So this is a scatter plot in the green color, for example, for the left. You can see that the green histograms represent the distribution of the genuine scores that are the bona fide scores. So genuine scores is when we compare inward subject with the same subject. So that is genuine. And in the blue, we have like a zero attack, zero imposter score, zero attack imposter scores. That means that we assume, like for example, if you have 50 subjects in your inward system, we assume for one subject, another 49 will act as a zero effort imposter. So that is an imposter scores in the blue. And the what you see in the other color here is the attack scores. You can see that the attack scores are closely coming towards the genuine scores. It lie between the imposter and it lie between the imposter and genuine, and also it will closely overlap some of the genuine scores. So this is same with all type of attacks, all three types of attacks what we have generated. So that means that attack what we have generated is capable of spoofing a biometric system, especially the face recognition system. So we have presented a couple of approaches, but approach one look like this. So we simply take multiple depth images and then we do the face detection and all the pre-processing, alignment, so on and so forth. Then we compute the simple focus measure. So when we compute the simple focus measure, so we use different kind of focus variation. So our idea is to see how focus change from different images. So what is the rate of change, how it is changing, can we use those measures to see whether we can identify bona fide versus artifact. So we presented three different kind of things here. So which is max minus min or ratio of that, or we use both focus measure as a feature vector and then send it to a classifier. Classifier what we use is a two-class split classifier. So basically the presentation attack is a two-class problem. So you have a bona fide or you have an attack. So we also present an second approach. So second approach is mainly looking towards only the depth image. So what we identified when we are working with this kind of cameras is if these cameras could not record more more variations in the directions of the light, through the micro lenses, then obviously the number of focus image they render is always less. So if they could not quantify, or if they could not capture more directions of the light, then it won't give more number of images. So we just say, okay, why we need other, why don't we use just like a simple number of, just like we count number of depth images and say like, well, how much we can achieve the classification of bona fide with presentation attack. So if we can achieve a good result, then probably we don't need any kind of presentation attack detection scheme. We just say like, okay, this is the count we have, then it is bona fide. If we don't have this much of count, this is an attack image. And then we benchmark the results with several existing techniques and so on and so forth. But we see that just counting image does not work as it is expected. But however, the variations of the focus or the rate of change of the focus within the different focal images can be used to identify these kind of attacks. Well, another important thing what we try to explore is the multispectral, right? So multispectral is an existing technique, so it's existing thing. So it try to analyze the reflective properties of the materials basically. So the human skin has a very different reflective properties, and the artifact materials what we use is having a very different properties. So if we just say like, if we try to analyze the reflective properties of these materials, is it possible for us to achieve the generalizability? Because the real challenge in presentation attack is to detect the unknown attack. That means that if I devise or design my system with some of the known attacks like print attack or the display attack and something, and tomorrow if someone comes with a mask, then I should detect it. So therefore we thought like, okay, why don't we try multispectral camera and see like, can we quantify these kind of materials from the human skin? So that motivates us to use the multispectral camera. So for that we use the spectral cam. So it is capturing like seven different spectral bands. So we are starting from 425 nanometers to 930 nanometers, and this is how the different images will look, and this is how we capture the image. But what is quite interesting, before we start working on this in 27, there exist one or two literatures which are discussing on this kind of attacks with multispectral camera. Basically, they try to use just two bands with visible and one in the near infrared, but not like multiple bands within the range. And it was somehow shown that at near infrared, it is difficult to deceive the system. So that is natural because most of our face recognition system are designed to work in the visible band. And obviously, if you are trying to probe the near infrared images, especially in the low quality, obviously the information is completely different and system cannot perform well. That is a well-known problem, because there are several papers, tons of papers that exist, like how to match the visible image with near infrared images and so on and so forth. So here, what we try to do is like, we try to see how about training a system with near infrared image. So we have our own face recognition system trained on the near infrared images as well as the visible image. So it is a multispectral face recognition system what we have used, and then we try to see the generated attack is creating a vulnerability or not. So you can see here at different bands, we see a lot of vulnerability because you can see the genuine scores are overlapping with the artifact scores. If you see the table here, IAPMR is imposter attack presentation match rate, which is also called as SFEL, the as spoof false acceptance rate. You see that higher the value is higher the vulnerability of the system. So here you see that especially with the inkjet kind of attack. So as I already pointed out, the inkjet kind of print is of very high quality. So it can be used to deceive face recognition system. So it is proven here. So even if you use a multispectral face recognition system, you can still spoof this system with inkjet artifact. Similarly, with the laser print, we show that it is consistent with state of the art, because state of the art will also say that it is not possible when you have a low quality attack. So we see that it is just 1.25%. So it doesn't matter. So if you're running your near infrared face recognition system, the presentation attack, the low quality presentation attack will never deceive the face recognition system. So we identify this, and then we check like, is it easy to detect the face easy to detect these kind of attacks using some basic texture-based features and so on and so forth. And especially at near infrared thing, so we identify that okay, it is quite reasonable with some of the values here, quite reasonable to identify these kind of attacks. So then we identify that why don't we use the spectral signatures? So the spectral signature is a unique characteristics that people in different applications like remote sensing and other kind of fruit analysis or so on and so forth, they try to use a simple spectrogram and see the characteristics of the materials. So we thought, okay, why don't we use that? Because what we thought is like if we can extract a proper spectral signature for the human face, then it is quite easy for us to distinguish it from the artifact because the materials has different kind of spectral signature. So to that extent, so we proposed a system so where we try to extract a spectral signature from 4 different points. And if you see the figure, this is how the spectral signature profile will look and for the bona fide, and this is how the spectral signature profile will look for the artifacts. So however, the spectral signature itself is not very indicative because when we capture the face, we have a lot of variation with the light, a lot of variation with the environment, and so on and so forth. And it is very normal with the face recognition system because most of them will work in the unconstrained conditions. So obviously, we found just from the signature analysis, it is not that straightforward. But however, we can plug in a classifier and see whether we can improve it and see whether this can be used for the generalization. So what we did is in this figure in the top, you can see that we have a spectral signature in the left, and we have different ways of combining the multispectral information. For example, we can combine at the image level. So you take like 8 images, you do the image fusion, and you have one single image which has all characteristics, and use that to detect the presentation attack. And the other one is the score level fusion. So you independently do LBP or something, and then you combine the scores, and then you say whether I can detect an artifact of bona fide. You can see that especially here in the first figure. So the attacks are well classified. There are some scatterings here, there are some scattering there. It is same here. There are some scatterings in between, but we can easily classify these kind of attacks. So this results we achieved when we train a system with known attack. That means that I know this is a print attack. I will train my system with a print attack. Then comes only the print attack. Then I will validate or test my system with that, and then I will present my result. So my system already learned on the print attack. So when you give the print attack, obviously it is highly robust in identifying it. So now we turn around and say like, okay, we train only on the print attack and we put up the display attack as in testing. So will that help? So obviously you can see here when we train only on the inkjet and we are putting up with the laser jet, it is quite difficult for the system to recognize this kind of attack. So that means that the generalizability, even with this kind of multi-sensing technology, is appears to be more challenging for the reliable presentation attack detection. So then we extend this study for the disguise attack. So disguise attacks is very much used in the real life application. So our intuition here is the same. So the disguise materials what people will use is different than the natural material. So how can we identify these kind of attacks? So we have developed our own database, and we also custom one sensor especially for this. So it can capture now for 8 different bands. So previously we used just 7. So we have collected our own database with different disguises, and then we compute again a simple spectral signature across the mustache, because when we collected a database, we identify that some of the data subjects does not have a mustache. So then we need to balance the database. So then we have, okay, so we cannot use the full image. Then if we use the full image, then possibly the system what we propose may not do the disguise detection. It may do like with mustache, without mustache, with beard, without beard, something like that. So in order to compensate that, we make sure that the database is of mustache, both real as well as the disguise. And then we crop the face image. So once you crop the face image, obviously if you have a long beard, so it will appear something like this. So most of the disguise will automatically taken care. And so we do the analysis only in the mustache region and then compute the average signature, and we propose a deeply coupled autoencoder for this. And then we show that how the signature is differentiated. So if you just take all the blocks, average it, and you plot it, so you can easily see that the bona fide signature is very much different than the disguised signature. So it's a kind of large scale database. It's publicly available. If you're interested, you can look into this paper and download the database and continue the study. But we achieved like 3% of equal error rate in this. So other kind of technique what we have used for this is the 3D sensing. So we used a very low cost 3D sensing. So it is a Kinect camera. So it has both RGB and a depth image. For this we use a mask attack. So this is not a silicon mask, but it is still a better medium quality mask that can deceive the system. We also shown that this kind of mask can create a vulnerability also in the paper. So what we try to do is like when you wear the mask, there is a small gap between your eye region and the mask region here. So because these masks have a hole here, so therefore we try to explore that. And another observation what we noted with this kind of mask is your nose is not always proportional. So the real nose of yours and the mask nose of yours is kind of deformed. So we identify those kind of local features and we devise a system to capture the local features, especially in the eye region and especially in the nose part and so on and so forth. And together that we also use a global feature. So for the global feature, we use any kind of texture. For instance, in this part, we use BSIF kind of texture features. So, and then we combine them and then we see the results. So for the demonstration, you can see the video here. So you can see that, okay, so this is same. So now you can see here the real face is accepted by the system, is the real face here, and the spoof face accepted by the system. So for example, if I don't run my presentation attack detection, then how the face recognition system is accepting these images. So whenever you see the red color here, it is successful attack. Once I plug in this system into the action, then automatically you can see some of them are detected. So you can see now system is in action. You can see the vulnerability of the face recognition system. Almost all the mask attacks what we give is getting successfully accepted by the face recognition system. But once you plug in our system, then you can see that we can automatically successfully detect this kind of presentation attacks. So depending on the mask, so if you change the mask, obviously this system may not work because it is tailored basically for the database, I believe. So because we identify that the mask was not properly prepared, there is a kind of deformation in the mask, and we try to propose a technique that can identify this kind of deformation. And we also clearly notice that there is a huge gap between the mask and the real eye. So we try to explore those kind of issues. But however, the database is also public, so you can benchmark your results. So then we move to the iris with our research project. So our idea is to have the same kind of multi-sensing for detecting the iris presentation attack. So there exist no systems for the iris, no multispectral iris, because iris recognition system is very much convinced by all kind of users, starting from security people, border control people, and so on and so forth. And it is well known that it works amazingly well in near infrared imaging in a very constant conditions and so on and so forth. So therefore, there exists no practical or no commercial device that can give you a multispectral iris recognition system. But with near infrared, just with near infrared, so recently they have shown that the iris recognition system can also be deceived or also be attacked with new kind of artifacts. But if you say like in near infrared system, I am presenting iris with a print attack, then I think it is quite easy to detect those kind of attacks with simple software. But if you have a very sophisticated attacks like the display attacks using a special kind of display like a Kindle display and so on and so forth, obviously it is not easy to detect those kind of attacks. So that is the motivation why we need to design these kind of sensors. So we have designed our own in-house sensor, so you can use that sensor to capture yourself an iris image. So it is an handheld device, and we use simple aluminum balls. So because we try to have this artifact eyes in a real manner, but we could not achieve it. So then we simply took some Halloween balls and then we prepared an attack system for this to see like can we do these kind of attacks on the iris recognition system, and we see like whether we can detect it. So you can see that our system is running in near infrared band. We are not going to the visible band because when you shift from when you have a whole range of visible to near infrared, then image quality matters a lot because the focus will change, because what you fix the focus for visible may not work good for the near infrared because of the illumination change. So the focus is different. When we do face, it does not matter, but when you do iris, it kills the performance of iris recognition system. So our idea is to use the existing iris recognition system together with our solution. So our solution can do both recognition of iris as well as presentation attack detection. So that is the motivation why we stay within the near infrared range. So here is the image what we have captured. So you can see that there is a nice structure of iris that has been captured here, but when you present the artifact, you can clearly see the quality of such artifact is too less, therefore it can be easily detected. So we present some of the very basic method like LBP, SVM is quite enough to detect these kind of attacks and so forth. And most recently, so we try to work on finger vein sensing. So finger vein sensing is quite popular since for past 8 years because no one can see how your finger vein will look, right? So since no one can see how your finger vein will look, it is very difficult to spoof unless you cooperate with the attacker and get spoofed. So there is no other way you can get spoofed with your finger vein biometric system. So, but however, spoofing finger vein biometric system is also not an easy task because it works in near infrared imaging. So because we cannot capture finger vein invisible, you need to go to the near infrared imaging with one particular spectral band. Particularly, you need to penetrate a light on your finger, and then you have to capture the reflections from the penetration to have a finger vein image as shown here. So what we thought is like, okay, so why don't we have kind of intuition that if we change the light, then if we change the intensity of the light, then the reflection from the artifact and the real image might be different. Because if you have a glossary artifacts which are presented, or if you have a very solid artifact which is presented to the finger vein system, then obviously the intensity of the light should give some intuition on how we can detect it. So to this extent, we developed our own sensor. We have our own sensor. So we then capture our fingerprint image with different artifacts. So we used a print attack. So because we capture our finger vein image, we print them with a very high quality printers, and then we also make sure that the finger vein pattern is highlighted with the marker. So because otherwise it is very difficult to check. So for example, you see in the figure here, so here you see that how the artifact finger vein will look. So then we introduce, since we are having a multiple light intensity, we introduce the SFS net. Uh, so SFS net is nothing but it's a well-known deep learning technique that will be used for shade from that is used to construct a 3D form shading. So basically it is a network. There is a deep learning network that will accept one image and it will decompose and give the normal map, diffuse map, and lighting parameters. So it is very widely used in 3D applications for this. So we just use, since we are working with the light, so we are more interested to look into the normal and the diffuse map to understand how this light is scattered and diffused. So we just plug in the existing SFS net. We did nothing out of it. So we just plug in and then use that SFS net as a feature extractor. So you plug in the SFS net, pass the image, you get number of normal maps and diffuse maps. On this normal map and the diffuse map, you just extract a simple texture-based features, and we show and do the classification using SVM, and we show that it performs perfectly all right with the database what we have captured. So this is all we are. This is the direction we have taken for the hardware-based approach. However, for the software-based approach, we are mainly focused on proposing different kind of descriptors, especially for quantifying the presentation attack. So to that extent, we also presented a new kind of descriptor which can be used for different applications also, but we particularly tailor this new descriptor for presentation attack detection. So we call this as LAMP features. It is basically a multi-scale texture feature analysis what you have proposed. So with this analysis, we try to analyze the given face with the different orientations of the textures and different scale resolution of the textures, and then to identify whether it is a bona fide image or an attack image. However, the code is also available, so you can check the paper and download the code if you want to use it. So we use the public database, so it's not our database, it's a publicly available database, and then we benchmark our performance and we show that ours is the best performance. And you can also see some distribution of the scores, so with the different kind of decisions we have made. So decision fused is in blue color here. It is an independent decision. So with the visible and near infrared is for the multispectral. That is two spectral, near infrared and visible. So we show that okay, with our proposed features and the fusion, we can achieve the better results. And the recent directions what we are taking in the software-based approach is mainly on solving the cross-camera and cross-PI detection. So if we say today I am going to develop a new technique for presentation attack detection, then it is very much essential that we try to address these two things, a cross-camera as well as cross-PI detection. Cross-PI means you train on one artifact, you test on other different types of artifacts, and then you make sure that what we are proposing is a kind of robust, also generalizable solution. Because if you go with the hardware, the solution can be easily achieved, but with the software, if the scalability is high, it is very challenging for us to achieve the solution. So in this most recent work, so what we try to do is we try to use a cluster of pre-trained networks which are already existing. So the first thing, as I already mentioned, we don't have a very large databases publicly available to train our own network, but however, we can use the deep learning techniques all together as in feature extraction or as in fine-tuning techniques. So in this work particularly, so we just use 6 different networks as an feature extraction technique. So we don't do anything. We just take off-the-shelf ImageNet-based trained systems. We pass our image and represent the features from them, and then we propose a new way of combining the features from this off-the-shelf deep CNNs. So what we try to do here is called as SLUG, that is spherical interpolated features. When we have 2 feature vectors, we try to combine them by interpolating them to the spherical space. So once we interpolate them to the spherical space, the discriminator of the bona fide and the attacks are very well qualified. So that's the reason there are several ways of you can interpolate. You can use the sine to estimate the angle between them, or you can use the cosine to do it, but we evaluated sine and cosine together, and we identify that use of this kind of interpolation as performed much better than the existing most recent deep net. So this kind of deep learning network, so for example in the reference 5 what I am pointing now is based on the extract of ResNet. So the present trend in deep learning is basically right, when you have a small database, it is not essential that we can train a fundamental network. So what we try to do is we take some existing network with some existing weights, and we try to augment some of the networks, and we freeze some of the layers, and then we try to train these networks to achieve the better performance. So most of the directions in presentation attack is using a small extract from the ResNet or using a small extract from exceptional net or something like that. So these residual architectures are getting more popular here. So this is based on such an architecture, and this is the most recent one. So from 32%, we try just by using SLUG interpolated based feature fusion and the stack of neural networks, we can achieve more, we can achieve the best performance. So the challenge, as I already pointed out, so this is what the people has to do now. So because most of the known attacks are already solved in the domain. So now other kind of software-based approach, what we explored long before, other than face, is also based on the iris. But this is in the very early in 2014. We just to see that, okay, can we use simple frequency-based features or so on like that? Yes, it is possible. As I already mentioned, when we talk about iris recognition, it works in near infrared. That itself is an advantage to detect presentation attack detection. So most of the presentation attacks based on the paper, display, and so on can be easily detected using these kind of attacks. So this kind of sensing, especially in the near infrared. So we did the same for on the publicly available database. This is available MYST database probably. So it is available publicly anyway. So we show that simple use of simple frequency-based methods as well as some texture features can solve this problem. So another interesting problem with the iris is identifying the contact lenses. So because if you can wear a textured contact lens, you can conceive yourself from the iris recognition, because iris recognition will sense your textures printed on the contact lens, and then obviously it will fail to recognize you. So you can do a concealing attack on those kind of texture-based on those kind of texture-based contact lens. So therefore, the texture-based contact lens detection is quite a challenging problem now, but it is quite easy to solve, because the texture what you print is easy to detect with any kind of texture feature extraction. But if you want to consider the texture contact lens and also the normal contact lens together, then it will become a three-class problem. Then it can pose a little bit more challenging, because having a contact lens on the eye, normal contact lens on the eye can also deceive the performance of iris recognition system. So if you are carefully looked into the any of the commercial iris recognition system, the presence of contact lens is very important, and it is considered as one of the quality features before performing an iris recognition. So therefore, detection of both of these lenses are of equal importance, especially from presentation attack detection, also to improve the reliability of iris recognition system. So this work, what we presented here, is a stack of some linear filters, and these filters are learned using independent component analysis. So this is similarly like, so if you recall from the today's first class, so in the first layer of deep learning, we try to learn some low-level features, right? So these features will look like a Gabor filters, if you recall, if you have seen the Gabor filters. So similar kind of filters can also be learned using different kind of techniques. So one kind of technique is using an ICA. You take a natural images altogether, you make a patches of these natural images, and then you compute the ICA. From the ICA, you take the stack of top 20, and then those will act as an filters for your image representation. So you use those as in filters, you convert the image, you extract the image, and then you process them and have a linear SVM and combine all the decision together. So this is basically a three-class problem. So we have compared our proposed method with different things, and then we show that, okay, so use of this stack of filters, of course it's highly computational, no doubt, can improve the performance to the certain extent. And in the next work, we thought of proposing a simple, shallow serial network. So we identify that, okay, so if we, rather than processing the iris region as a single image, why don't we use them as a patches? So if we use iris image as in patches, so can we come up with a new architecture that can be used to detect these kind of attacks? So this is a simple three-level architecture. So it is mainly inspired by the architecture of AlexNet, with similar kind of thing, but with different kind of parameters. And we show that, like, for example, if you see this figure, these are the activations that we extract on the second convolution layer here. So some of the some of the low level features, what you can see is the blobs kind of the features that are almost representing the presence of a kind of boundaries between the boundaries between the texture contact lens and normal eyes. So we then benchmark the contact lens what we have proposed here. So we achieved a little bit of performance, but as a three-class problem, okay, so this can give some input. So then with the finger vein biometrics, as I already pointed out, so it is not easy to perform an attack on a finger vein biometrics, because if you just take the printout of the near infrared imaging, obviously you don't get a very good quality, right? So you need to devise how you do the attack. So you have to generate a different kind of blocking device, because as you know that the finger, when you attack a finger vein device, the light will be given from the either sides or it is from the top. So because light needs to penetrate inside the finger to capture the image. So therefore you need to block these lights. So to block the lights, you need to devise a kind of special device with certain things. And then you put up your print of the finger vein with little bit of modifications and image enhancement and so on and so forth. And then you present it to the system. So then you see here the vulnerability of such a attack here. So it is not even penetrating deep towards the genuine scores, which shows that it is quite challenging to do that. But still, it is reasonably coming into the border of genuine score distribution. It is same with all three types of attacks what you have done, especially with the display attack what we had here. So it is almost like penetrating the genuine scores here. So this is a kind of challenging we had. So, but however, we are successful in deceiving finger vein also. So then we proposed a steerable pyramid feature. So it is similar to the wavelet features, but you can steer it in different directions and get different scale space features. So then we benchmark with different kind of techniques and so on and so forth. And of course, the use of these kind of texture-based methods, especially in the near infrared, works pretty well. So other kind of technique what we have used is on the temporal information. So since we have our own device, we can also collect the video of the finger vein what we have captured. So once we collect the video of the finger vein, what we try to do is can we see the motion of the blade in some way? So is it possible to see the liveness feature from the video? So can we process the temporal information and see that? So to that extent, we use the modified EVM. So EVM is Eulerian video magnification. So these techniques basically do a lot of amplification on both spatial as well as the temporal information, so that even the small information or the small motions in the video can be accelerated to the higher motions. So we just modify those methods and we presented a presentation attack detection model. If you can see the video here, so on the left we have normal images, and this is how the presentation attack detection scheme is working. As you can see, as we process, as the video is coming, our proposed method can identify or enhance where the finger veins are present. So you can see here the thickness of the vein is extending as we proceed further. So you can see that it is more enhanced here, while in case of an artifact, you don't see any kind of magnification here. So with the temporal information, we simply compute the optical flow and say the change in the motion is quite indicative here. And you see that in the end of the video, so you can see here, so it is highlighted too much where there is a motion of the blade. So we use two different kind of artifacts here. So this is artifact 1 and this is artifact 2. And we collected our own database with a lot of videos and so on. And we evaluated our proposed method, and we show that, of course, even though the results are so clear, it is not that easy to get 100% results. So it is not still solved. So we still have like 3% AC here with these kind of motions. And other directions what you took, especially on the software-based approach, is on augmenting the existing network. So since we don't have enough images, what we try to do is like we try to use the pre-trained network. For example, in this work we use AlexNet, and then we augment the AlexNet with more number of layers. So for example, with FC, number of FCs and dropout and so on. So by doing that, we are trying to adopt the existing network to our problem. So and then you try to fine tune these layers and then see whether you can improve the performance. So compared to the previous liveness measure what we have presented, so use of this kind of networks are really quite easy to identify these kind of attacks. So where are we now from these things? So the known fact in presentation attack is very well defined. So what is known in the community today is hardware-based solutions are known for robust performance. So hardware solution is capable of detecting known and unknown attack. But however, the usability, cost, and maintenance is very high. So that means that the the usability is very important, because if you say like I want to develop a presentation attack detection for border control, usability is very high, and especially you want to do it in fast time. So you cannot hold a passenger for a long time to do a presentation attack, right? So when you have a multiple hardware based solutions, obviously it take more time. And sometimes because hardware based presentation attack, what I indicated to you here is just on the imaging, but there are several ways how you can measure the presentation attack. They have other kind of sensings. They can have the pulse measurement. They can have the other kind of things. So those things with hardware will not so convenient for the user, especially from the time, especially also from the interaction. And of course, the maintenance is always high. On the other hand, the software-based approach are very cost-effective, but it lacks the robustness because the variation in the data is too high. So especially with the face recognition system. So software-based approach for fingerprint biometric systems or with the iris biometric system can work perfectly all right. But when you go to the face recognition system, variation of the different sensor, variation of image are captured completely unconstrained will make this problem more challenging. And use of low-cost sensors are already shown some of the reliable results, especially on the print and display attack. So there are several works that indicate that use of Kinect or simple Intel RealSense camera with 2.5D is capable of differentiating 3D structure of the face with 2D structure of the face. So that is possible. So if that can do, then it can immediately address or solve the print and display attack. However, with the availability of large-scale database today, and with the multi-queue techniques that I already mentioned, like not just using one type of feature, so you try to use motion, you try to use texture, you use multiple texture-based methods, and so on and so forth, and then combining all of them can be used to achieve the generalized solution, but still it is quite challenging. So what are the open issues we have today? So the most of the work concentrated in the literature is focused on having a special hardware or focus on developing a software. However, these things are not adopted for the consumer devices, especially the low-cost smartphones. So if you want to have solution to the low-cost smartphone, especially in the countries like India where they want to enable Aadhaar card authentication on the smartphone, then it is very essential that we need to have this kind of solution to be worked on smartphones. So then when it comes to the smartphone based technology, it is because the computation source is limited, we cannot use additional hardware, we cannot use additional queues, then the challenge of presentation attack remains as it is. And the generalization to the unknown attack. So when we talk about the attacks, it is always a cat and a mouse problem. So we provide a solution, there comes a new attack. If we provide a solution, there comes a new attack, right? So when we never know what type of attack can emerge in the future, it is very challenging for us to devise a solution. So that means that we need to see like how certain features of the bona fide sample itself can be used. There are some directions in this. The use of anomaly detection, use of one class classifier has already taken some path, but still it is very challenging just to rely on those techniques. So possibly use of one-shot learning or the few-shot learning, only quantifying the bona fide samples may be in possible directions. And then robustness for data capture quality, environment, demographic bias, and PIS. So all of these are a big problem in itself. So how your presentation attack detection works when you have a change in various quality of the image, different environment. And how about the demographic bias? The database what you use, you train it on one set of gender, or you train it on one group of people, right? So for example, if I stay in Norway, I try to build my system on the data what we collect in the Norway. If you stay in India, you try to train and build on Indian database, especially who stay in China, who try to train and build on the system. So then comes a huge challenge, right? The system never see the bias in the demography. So obviously the demographic bias is a huge problem that need to be addressed not only from the biometric recognition but also from the presentation attacks. And the PAIs, the presentation attack instrument. So we know that okay, the print can be generated in one way or the two way. We never know. Every now and then new printers, new way of technology is improving, the way of printing is improving. And so there exist several PAIs which can come. So when we think of providing a solution, it is always good we think of more providing towards a generalizable solution. So these are all the open issues, at least so which are still open and people are trying to address this. So this is the possible directions one can take. So before I finish this, so I would like to acknowledge my students, colleagues, and mentors, and then some funding agencies, and then I am done with first presentation.